Okay, so now I give you an intuition about quantum source compression, but now after the intuition, I want you to give you a scheme. So let's go to the quantum compression scheme that's just um, take on the intuition. So the compression scheme like could be like you have your source, um, can be a photon source or whatever else. So I'm accommodated with photon source for now. So just say the photon source, it's made photons, gives you a state, second on, px2, let's give you px2, and after it give you pxn, and give you pxn. And so you have all of this, and after, yeah, it gives you your state, as earlier, but so I didn't say earlier, but it's IID, all those stuff, it's uh, identical or indistinguishable, like, how can I say it? It's like, um, independence and identically distributed. So independent for the first term, so which means each step does not depend, like first source does not depend on the second one, etc. Does not, like, this will not imply have a consequence or the second source, and second source will not have a consequence on other sources. So they are all independent, and they are all identically distributed. What the first box source like do will not have a like identically distributed, just like each box produces the same type of states with the same probability. So they're less or more the same, have yours. So you produce a state with a certain probability, but they are naturally different ones from each other. So yeah, independent do not have implication on each other, and identically distribute, like they're the less or more the same. And so after you have your states, and so as you say, like we wanted like to do compression, and to do compression, it's like, I don't know, like it's like here it's like A, like it's A B. We already take the step of earlier, like it's like A B B B B 5 times, and like after A, or like, yeah, I think, I don't know if I write A or in the other sense, but it's like, and after B B B B B with each state representing a letter, for example. And so yeah, so you have your encoder, and so yeah, you have your 10 stuff here, and so the encoder just from it can find a message from here that will call like psi b to the power of n to the power of m, maybe to be with m being like m qubit state, instead of n. And so the goal is like to make m as small as possible. So yeah, and at the beginning we have like, we'll say we have like n. Here we just want to have um, m being strictly referred to n, as small as possible. And so in our case, so it will give this. So in our case, like it's CBM, and so in our case, just like 5i 5b. And so if you take the decoder after, then we can reconstruct our states, so that's perfect because compression, there is no loss of information here, and it's and you try to regate your stuff into eggs or m. So yeah, in the way the encoder, just go from LA 0n to L to C to M, but the decoder go to LA LT like C to 0M, and try to recover LA 0M. And so yeah, that's what you get about. Let's see here, we have 5B. And so the decoder just recognizes it, and so it can rewrite the initial state with the 5A and the 5B. And here, we just have 4 qubits, like each letter representing a qubit. Like we just compress the information. At the beginning we have 10 information, after we have 4. And so physical, like here it's not qubits, like physical letters, but that's the idea. And yeah, that's cool. In a way, it's just like if we have just take the elementary information and remove the superfluous, like the ones who are not really elementary ones, um, and remove what is unuseful, and so what is redundant, and so you just have A and B at the end, and the number of time, and so you reduce to 10 to 4. So that was the example with which was more the deterministic approach. But if you take the head and the face, heads and tail approach, and we try to replay it here, like instead of having this a b, we can say like we can like launch like 1000 time our coin, so we can have like 0 1, and after 6 3 like 0 0 1 blah 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 1000 time, and so that can be our cats. So at the end, like it will be like stuff will be written like 0 1 blah 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 0 1 blah 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 0. It's like the 1000 inside, and because of law of big numbers, that in 99.99 cases percent of the case, like our suite will will contain most of the time less or more 500 head, 500 tail. The some suites, like to be precise, will be like will never be like 1000 head or 1000 tail. It will like less or more never happen, and we can just ignore it and go into the typical subspace. So you have your space, and it's just like relay. Well, it's a difference of relaxation, but it's the opposite stuff, because relaxation, you take a bigger stuff, and after you close and close. And here it's different, like you have a bigger stuff and you take less close, so you can ignore what is not important. I thought also information where but it's not the same too, because you encounter information too, but like it's more like you have 0 and you want 0 0 0. But yeah, you try to reduce the number of qubits, but like it's the other sense, so less or more. Have one physical logical qubit, and you have 3 physical qubits. It's not so you look at it, but yeah. So yeah, the goal here, you have 0 1 1 1 0, and so you just take this typical state, and instead of just checking, we see it's like 1/8 when you have it's 1 to the 2 of the power of n possibilities. So with 1000, it's 1 divided 2 of the power of 1000. We just will check about codes to sequence that work, so that have like 50% of chance to occur. Uh, and so we can say like it's an example. I don't know if it's accurate, but instead of taking 1000, at the beginning we'll have 1000 staff, we'll take only 900. um, and 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 yeah, uh, we have like 900 bit compressed, and the decoders like try to receive those 900 qubits and check the code and try to replace the 1000 qubit into the Hilbert state. Um, so if it was okay at the beginning, like the original was classical, the decoder can recreate exactly the same pipeline, same beginning. If we had like 1000 time, so I am here like you go from before we go from 10 to 4, and now we just go to 1000 to 900. Here it was like this more totally accurate with the first example. Here compression will not work when we have only zeros, only one, but this is so rare, so it's not it's most of the time will be less or more every time okay and all right, and we just have economized qubits and removes like the unexpected cases, and be so being like more fast in a way, and having less or more the same results approximatively, even if it's a little better with the other one, because you can take the case that never happen less or more but can happen, but yeah, it's less or more the same because they less or more never happen still.